Quantization or Quantization of Charge 1.4. Proving that atoms actually existed was a big accomplishment, but demonstrating their existence was different from understanding their properties. Note that the Brown-Einstein observations had nothing at all to do with electricity, and yet we know that matter is inherently electrical, and we have been successful in interpreting certain electrical phenomena in terms of mobile, positively and negatively charged particles. Are these particles atoms, parts of atoms, particles that are entirely separate from atoms? It is perhaps premature to attempt to answer these questions without any conclusive evidence in favor of the charged particle model of electricity. Strong support for the charged particle model came from a 1911 experiment by physicist Robert Milliken at the University of Chicago. Consider a jet of droplets of perfume or some other liquid made by blowing it through a tiny pinhole. The droplets emerging from the pinhole must be smaller than the pinhole, and in fact, most of them are even more microscopic than that, since the turbulent flow of air tends to break them up. Milliken reasoned that the droplets would acquire a little bit of electric charge as they rubbed against the channel through which they emerged. And if the charged particle model of electricity was right, the charge might be split up among so many minuscule liquid drops that a single drop might have a total charge amounting to an excess of only a few charged particles, perhaps an excess of one positive particle on a certain drop or an excess of two negative ones on another. There's a nice picture here, a simplified diagram of Milliken's apparatus. Milliken's ingenious apparatus, shown in the figure, consisted of two metal plates, which could be electrically charged as needed. He sprayed a cloud of oil drops into the space between the plates and selected one drop through a microscope for study. At first, with no charge on the plate, he would determine the drop's mass by letting it fall through the air and measuring its terminal velocity, i.e. the velocity at which the force of air friction cancelled out the force of gravity. The force of air drag on a slowly moving sphere was known to be BVR squared, where B was a constant. Setting the total force equal to 0 when the drop is at terminal velocity gives, okay, you see an equation, which I should probably pause and read if I'm hearing this, and setting the known density of oil equal to the drop's mass divided by its volume gives a second equation, as you see. Everything in these equations can be measured directly, except for M and R. So these are two equations in two unknowns, which can be solved in order to determine how big the drop is. Next, Milliken charged the metal plates, adjusting the amount of charge so as to exactly counteract gravity and levitate the drop. If, for instance, the drop being examined happened to have a total charge that was negative, then positive charge put on the top plate would attract it, pulling it up, and negative charge on the bottom plate would repel it, pushing it up. Theoretically, only one plate would be necessary, but in practice, a two-plate arrangement like this gave electrical forces that were more uniform in strength throughout the space where the oil drops were. The amount of charge on the plates required to levitate the charge drop gave Milliken a handle on the amount of charge the drop carried. The more charge the drop had, the stronger the electrical forces on it would be, and the less charge would have to be put on the plates to do the trick. Unfortunately, expressing this relationship using Coulomb's law would have been impractical, because it would require a perfect knowledge of how the charge was distributed on each plate, plus the ability to perform vector addition of all the forces being exerted on the drop by all the charges on the plate. Instead, Milliken made use of the fact that the electrical force experienced by a point-like charged object at a certain point in space is proportional to its charge. F over Q equals constant. With a given amount of charge on the plates, this constant could be determined, for instance, by discarding the oil drop, inserting between the plates a larger and more easily handled object with a known charge on it, and measuring the force with conventional methods. Milliken actually used a slightly different set of techniques for determining the constant, but the concept is the same. The amount of force on the actual oil drop had to equal mg, or m times g. Since it was, I don't understand this as I'm reading it, so hopefully I get it later. Since it was just enough to levitate it, and once the calibration constant had been determined, the charge of the drop could then be found based on its previously determined mass. Yes. The table on the left shows a few of the results from Milliken's 1911 paper. Milliken took data on both negatively and positively charged drops, but in his paper he gave only a sample of his data on negatively charged drops, so these numbers are all negative. Even a quick look at the data leads to the suspicion that the charges are not simply a series of random numbers. For instance, the second charge is almost exactly equal to half the first one. Milliken explained the observed charges as all being integer multiples of a single number. 1.64 times 10 to the negative exponent of 19 coulomb. In the second column, dividing by this constant gives numbers that are essentially integers, allowing for the random errors present in the experiment. Milliken states in his paper that these results were a direct and tangible demonstration of the correctness of the view advanced many years ago and supported by evidence from many sources that all electrical charges, however produced, are exact multiples of one definite elementary electrical charge, or in other words, that an electrical charge, instead of being spread uniformly over the charged surface, has a definite granular structure consisting in fact of specks of atoms or electricity, all precisely alike, peppered over the surface of the charged body. It says, in other words, he had provided direct evidence for the charged particle model of electricity, and against models in which electricity was described as some sort of fluid. The basic charge is notated E, and the modern value is E equals 1.60 times 10 to the negative exponent 19 coulomb. The word quantized is used in physics to describe a quantity that can have only certain numerical values and cannot have any of the values between those. In this language, we would say that Milliken discovered the charge is quantized. The charge E is referred to as the quantum of charge. Self-check. Is money quantized? Quantized. What is the quantum of money? Okay.